This engine rewrote racing history. This secret almost destroyed Chevrolet. It wasn't just revolutionary, it was a ticking time bomb. It's praised as a superpower pack by day, cursed as the oil-starved assassin by mechanics at night.
Oh, why did drivers risk their lives for it?
How did it crush forward on the track while tearing itself apart from within? The truth is darker, deadlier, and more dramatic than you've ever been told. Birth of a revolution, Ford's Y block wasn't just competition. It was humiliation. Studebaker, they had a Valvetrain. GMS sales kings stuck with six-cylinders, while percent of buyers demanded VGM manager Thomas Keating's memo was a scream for survival. Flint, Michigan became ground zero, but who could design an engine to save Chevrolet? About percent of new car buyers wanted a V. By that number had climbed 2%. By half the market was demanding vengeance. Chevrolet's general manager Thomas Keating didn't mince words in a memo to GM's top brass. We've become too six-cylinder minded. His warning rang alarms at GM headquarters, sparking a decision that would become known as GM's billion-dollar gamble. New factories were purchased, including massive facilities in Flint, Michigan, to birth a V that could reclaim Chevy's crown. Edward Kelly, the revered engineer behind Chevy's legendary Stovebolt, was tasked with designing the new engine. Kelly was well respected, no doubt about that. But by the early S, many around him believed his ideas were starting to feel a little outdated. The first serious attempt at a Chevrolet Wunder, his watch was essentially a downsized version of Cadillac S, which had been launched in Kelly's version Displacement and was nearly ready for production when a major shift happened. In May, a rising engineering star named Edward N. Cole was brought in to take over the project. Kelly was reassigned to oversee manufacturing, while Cole took charge of breathing new life into Chevrolet's engine program. And it didn't take Cole long to spot a problem. Cadillac style, V8's too heavy, too costly, and had almost no room for future growth. Cole knew this wasn't just about horsepower. It was about building an engine that could be mass-produced efficiently, cheaply, and with room to evolve. He realized Chevy needed not just a new engine, but a new way to build engines. For Cole, manufacturing cost was just as important as any horsepower number or compression ratio. The mastermind and the clean sheet. Talking about the version developed under Edward Kelly, Cole didn't mince words as he reportedly said, "You don't tweak an old design. You start with a clean sheet of paper." And that's exactly what he did. And that clean sheet approach didn't just apply to styling or performance. It extended all the way into the engine's manufacturing process. Cole's team reimagined how to cast the engine block starting from scratch. He believed there were smarter, more efficient ways to build a better engine, more precise, more cost-effective, and still powerful. The breakthrough came with the decision to use green sand cores specifically in the valley between the bores. That critical squeeze angle at the heart of a V. Traditionally, engine blocks use dry sand cores. But Cole's team realized that by replacing most of them with green sand cores, they could cast the entire block upside down because it allowed them to precisely position the plate that held the bore cores, giving them tighter control over wall thickness. That meant they could safely cast walls as thin as of an inch. A gamaker for weight and efficiency. This casting method wasn't Cole's idea alone. Credited John Dula from the GM engineering staff, saying he had as much to do with that as anybody. Together, they pioneered a new block casting technique that allowed for unprecedented precision in cylinder bores and marked a major milestone in thin wall engine casting. At first, Chevrolet's new VVAs planned with cubic in of displacement. But engine displacement was rapidly becoming a bragging right in the S horsepower race. And to keep up with market trends and the competition, Chevy engineers bumped the number up to a range of 2 cub-in. Ultimately, the latter was chosen. One of the most important early decisions was setting the bore centers at in. That simple measurement determined a lot from the overall length of the crankshaft to the compact. Dimensions of the engine block itself, only in long, remarkably small, for a V final product was dubbed the Turbofire Van. It was more than just a marketing name. It represented a forward-thinking precision-engineered design. This new VAS over square, meaning its bore was larger than its stroke, which allowed for higher revving performance. It featured hollow push rods, stamped metal rocker arms, and an intake manifold that also served as the valley pan, a smart way to save weight and reduce complexity. Engineers built it with interchangeable cylinder heads, aluminum pistons, and a high compression ratio for the time. It also had fully water-jacketed ports, allowing for better cooling and wedge-shaped combustion chambers that improved combustion efficiency. And instead of using a cast-iron crankshaft like many others, Chevy opted for a pressed forged steel crank. Stronger, more durable, and a sign that this engine was built to perform. But the wasn't just compact, it was brilliantly engineered. It boasted a stroke-to-bore ratio of one of the best ever achieved at the time in an over-square design. That meant less piston travel per mile, lower internal loads, and most importantly, reduced wear on the piston's rings and cylinder walls. In other words, it was built for both performance and longevity. The engine also came with an in-toe-compression ratio, which was fairly high for the era. That boost helped improve both power output and fuel economy. A win-win for drivers. And thanks to the rise of higher-octane fuels, engineers were already dreaming of pushing compression ratios too in future production engines. Another standout feature is its compact block length, which is less than an that gave the engine incredible structural rigidity and left plenty of room under the hood, making maintenance and repairs a whole lot easier for everyday drivers and mechanics. One of the remarkable features of the was its wedge-shaped combustion chamber. This design included a large quench area, a flat surface that helped control detonation or engine knock. But it did more than that. As the piston moved upward, it forced the air-fuel mixture away from this quench zone, creating turbulence. That turbulence helped mix the fuel and air more thoroughly, leading to faster, more complete combustion. Chevy engineers also nailed the spark plug placement right in the hottest part of the combustion pocket. That meant the flames spread quickly and evenly, delivering smooth power with minimal risk of knocking. And they didn't stop there. A clever lip on the cylinder head extended slightly over the cylinder bore, acting like a shield. It protected the spark plugs from any oil the piston rings might scrape up, helping ensure reliable ignition every time. Engineering marvel or a Trojan horse. As compression ratios climbed during the S, engineers had to get serious about preventing detonation. But boosting compression was essential. It gave engines more power and better fuel economy, which was a win for both performance and efficiency. What made those higher compression ratios possible is the tetraethyl lead fuel additive that helped keep everything running smoothly without knocking. The cylinder heads were also interchangeable, so that meant no need to manufacture separate left and right versions, which simplified production and helped keep costs down. Clever engineering all around. The hollow push rods in the were a clever solution, allowing oil to splash up to the rocker arms and valve stems without needing extra oil lines or complex passages in the heads. While the concept wasn't exactly new, engineers had been using hollow push rods for decades. Chevrolet's execution still required innovation, especially when it came to the rocker arm mechanism. Engineer Harry Barr reportedly recalled there were problems with the hemispherical ball, the mating surface of the rocker arms, also in the amount of the oil that came up through the hydraulic lifters. One of our engineers, Bob Papin, came up with a little wafer, a method of metering that oil in the lifter, a little logjam that was essentially overcome. They also had to deal with uneven oil distribution between the rocker ball and arm. The solution? Designing a slight mismatch in contact surfaces so oil could properly flow between them. But even then, the job wasn't done. When the engine first hit production, some early units suffered from squeaky rocker balls and other teething problems. To address lubrication throughout the system, 3 horizontal oil passages were drilled into the block. 1 main gallery and 2 tappet galleries. Oil flowed from the high-pressure main gallery through a hole in the rear camshaft bearing shell and onto each tappet gallery, maintaining consistent lubrication even under demanding conditions. The stamped sheet metal rocker arm, a simple yet revolutionary piece, was originally developed at Pontiac by engineer Clayton Leachin while working on their engine program. Although Pontiac's engine didn't launch until due to several delays, Leach's rocker arm design would go on to influence the entire industry. When Chevrolet engineers began developing the small block, they consulted with their manufacturing team and quickly realized something big. The stamped rocker arm could be produced with 0 machining. That was a gamaker. It enabled a lightweight Valvetrain design, which in turn allowed the new small block to safely rev up 2 or even RPM. A big deal for performance at the time. But there was still one challenge: lubrication. As Clayton Leach explained in an interview with automotive historian Michael Lamb, Chevy had to drill a small hole in the pushrod socket to get oil to the rocker arm without flooding the combustion chamber. That tiny adjustment kept the engine reliable while still cutting costs. Even the rocker arm covers got special attention. Ed Cole, the chief engineer, wanted them to look as good as they performed. Within budget limits, he insisted they have style, leading to the now iconic Chevrolet script elegantly stamped across the top of each cover. Chevrolet's turbo Fairfee wasn't just about power. It was a study in smart, efficient engineering. One of its standout features was its fully water-jacketed ports paired with aluminum pistons, which gave the engine superior heat dissipation. This better cooling meant Chevrolet could use a lighter radiator, trimming both weight and production costs without sacrificing performance. The engine's autothermic slipper-type pistons fitted with 3 rings included a circumferential expander behind the oil ring. This ensured consistent axial and radial pressure to help control oil burning. Even better, the piston pins were press-fitted, a clever move that eliminated the need for a split rod and locking bolt, simplifying assembly. Thanks to its short-stroke design, the connecting rods remained compact. Combined with lightweight aluminum pistons, this kept the engine's reciprocating mass low, which improved response and efficiency. But it didn't stop there. Chevrolet engineers also revolutionized the crankshaft design. Using advanced forging techniques, they created a shorter, stiffer crankshaft that naturally reduced torsional vibration. Internal testing confirmed it. Vibration levels were consistently smooth across most of the RPM range with no sharp spikes. A harmonic balancer cleaned up the remaining resonance. To keep everything in sync, Chevy introduced new balancing technology. The crankshaft was first partially balanced using a machine with electronically controlled indicators. Then final balancing of the fully assembled engine was done on a separate device that could pinpoint the exact outbalance position. The solution? The machine simply drilled precise amounts out of the crankshaft counterweighs at the front and rear until perfect balance was achieved. Another key innovation that helped tame engine vibration was Chevrolet's poised power engine mount system, used on both the van to the 6-cylinder. This dynamically balanced 4-point setup was engineered to minimize how much engine torque transferred to the frame and body. The secret, the mounting points were angled so that the resulting roll axis absorbed most of the engine's movement, leaving only minor vibrations to reach the rest of the car. At the front of the engine, Chevy used strut-type mounts. Each one featured 4 circular rubber biscuits stacked around a metal spacer stud. These studs were secured to brackets at the lower corners of the cylinder block and sat perpendicular to the seat of the front cross-member of the frame. To reduce vibrations, the rubber biscuits were placed on both sides of the bracket and on both sides of the cross-member. At the rear, 2 shear-type mounts were placed at the lower back edge of the clutch housing, connecting the engine to brackets that were welded to the frame's side members. These mounts were made of 2 metal brackets separated by bonded rubber, which allowed the rubber to flex under shear stress when the engine rolled and under both shear and compression when supporting the engine's weight. The result, a much smoother ride and better isolation from engine vibrations. The deadly secrets. Yet for all its brilliance, this engine in its original form could kill itself from the inside out. One of the reasons is Chevy's decision to launch the without a full-flow oil filter. Flaw 1, the murderous oil system. The engine launched with only an optional bypass filter, filtering just % of the oil. Smokey Yunick, legendary builder, raged. Chevy gave us a great motor, but forgot to keep it alive. It was an oil-starved assassin. Prayed it didn't chew itself to death before me. Flaw 2, the expanding pistons of doom. Tight clearances saved weight but were deadly under heat. Pistons expanded, scouring cylinder walls. Mechanics dubbed it the scuffer. Southern heater track use meant near certain seizure. Flaw 3, missing essentials. No PCV valve, primitive breathers, rudimentary cam lubrication. Automotive historian Dave Emanuel confirmed that was a prototype rush to market. Chevy was so desperate to beat Ford, they shipped an engineer's dream and a mechanic's nightmare. The original turbofire relied solely on an optional bypass-style filter mounted externally. Instead of filtering all the engine oil, it only filtered a portion of it. That meant every time the engine was running, metal shavings, carbon sludge, and microscopic grit were free to ride shotgun through the entire lubrication system. This wasn't just a theoretical flaw, it was a time bomb. Turno were mounted fast, and many engines failed before their time. Chevy scrambled to fix the oversight and by the model year, a full-flow oil filtration system was finally standard, but the damage was already done, literally and reputationally. The piston design of the was equally bold and equally flawed. Built with tight thermal clearances, the pistons were engineered for efficiency, not endurance. In real-world driving, especially in the sweltering heat of southern states or when pushed hard on the track, those pistons would expand beyond safe limits. Result: scuffed cylinder walls, cracked piston skirts, and in severe cases, total engine seizure. Chevrolet issued technical service bulletins, warning dealers and mechanics to watch for overheating signs and to inspect pistons carefully. But again, the Band-Aid came after the bleeding. While later small blocks became paragons of design, the original was in many ways a prototype shoved into production. It lacked provisions for vital upgrades like a positive crankcase ventilation, which meant early versions suffered from crankcase pressure issues and increased oil blobby. The oiling passages were rudimentary. Breather systems were minimal. Mechanics quickly learned that retrofitting these early engines was a chore. Not because they were poorly made, but because they were designed in a rush to revolutionize. Even the camshaft lubrication system was primitive, relying on splash oiling in some areas where pressure-fed systems would later take over. Automotive journalist Pat Ganal wrote in the Small Block Chevy Bible, "It was a brilliant engine with a dark side. Chevy bet big, but they didn't sweat the small stuff." Why? It was still legendary. Despite these deadly flaws, the engine would go on to form the DNA of countless small block Chevy engines. In just weeks, Ed Cole's team of engineers, including Assistant Chief Engineer Harry Barr, turned a concept into a running prototype. By it was in production, offered in 2 versions for most of the model year. Buyers could pair either engine with a standard speed manual, an optional speed with overdrive, or the Powerglide automatic. The base featured a Rochester Aero carburetor, delivered horsepower at RPM, and pushed out pound-feet of torque at RPM, all for just $1 extra over the standard inline shortly after the model year began. Chevy introduced the Power Pack version, a hotter with a Carter 4-barrel carburetor, a special air cleaner, and dual exhausts. Except on station wagons due to fuel tank design. It churned out horsepower at RPM and pound-feet of torque at RPM, and it added just $0.00 to the base V cost, making it a performance bargain at $1 total. For second series Chevy pickup trucks, there was also a detuned horsepower version with toe compression. And just before the end of the model year, Chevrolet dropped a surprise, the Super Turbo Fire version boasting a full horsepower. Serious punch for the time. Compared to the 6-cylinder Chevrolets of and the Nouveau War, a massive step forward in performance. For context, a Bear equipped with a Powerglide automatic took around seconds to hit MPH, but swap in the horsepower. VF Rome, and that time was cut nearly in half, according to Motor Trend's road tests. It was a night and day difference. The response from buyers overwhelming. Chevy's new engine plant in Flint, Michigan was running flat out, but it still wasn't enough. Production had to be ramped up at the Tonawanda, New York, just to keep up. Even then, demand outpaced supply and Chevrolet actually lost some sales, because customers didn't want to wait for a Union model. Still, the appetite was clear. Percent of all Chevrolet buyers chose the VA number that proved just how right Ed Cole and his team had gotten it. The compact design, innovative casting, and scalability laid the foundation for Chevy's small block dynasty. Its DNA would power engines for decades, from Corvettes to Camaros. Track glory and bitter rivalry. Despite its self-destructive tendencies, the Turbo Fire was a track monster with the Super Power Pack 4-barrel dual exhausts. It dominated NASCAR. Herb Thomas won races including the Southern piloting the number Smoky Munich-prepared Chevrolet. Thomas reportedly said, "This little mouse has the heart of a lion when it stays together. You gotta nurse it, but boy does it run." Buck Baker won 3 races including the Charlotte Speedway event in the number Chevrolet. Baker was blunter. It made power Ford couldn't touch, but you listen for the death rattle every lap. Tim Flock grabbed poles in showing raw speed. Chevy snatched NASCAR wins in crushing Ford. The rivalry turned white. Ford engineers scrambled while Chevy teams lived in fear of the next engine blow-up. It was glory balanced on a knife's edge. What if's climax? The Turbo Fire is a story of brilliance, betrayal, and bare-knuckled survival. But what if? What if Ed Cole had just one more year? Would the oil-starved assassin have been stillborn, replaced by a reliable legend from day one? What if Ford's Y-Block hadn't forced Chevy's panic? Would the small block revolution have ever happened? Or would Chevy have faded into six-cylinder obscurity? What if those early failures had killed Chevy's reputation? Could Ford have ruled the S-muscle car era unchallenged? Is the unnecessary sacrifice, a flawed savior, or corporate malpractice disguised as innovation? Engine that one races and then self-destructed. Was it worth the gamble? You decide. This is Paul from Rare Car Stories reminding you to dig deeper, question everything. I will see you down the